over to what we call the filter group, and they have prepared a video, and then they're going to be available for discussion.
Martin?
Yes?
Should I share the video?
Yes.
Okay, then.
That's why you're here. And no one should worry about the timing. So we always have buffers. We know about this. So some of the breaks will be shorter and so on. Some student projects have dropped, and so don't worry.
Okay, can you see my screen?
Yes.
Okay.
Well, but we can't hear anything. At least I can't hear anything.
No.
COVID-19.
Okay, that's good.
Okay.
New name for the coronavirus. The World Health Organization has officially called it COVID-19.
This new decade greeted us with a pandemic that we have not seen the likes of in the last century. Drastic measures had to be met all over the world to reduce the spread of this virus. The scientific and academic world has also been in constant search for new and innovative solutions. The daily life of pupils at the classroom is one area where the problem of the spread of the virus is most prominent. The protection of this group is essential for our future. The AHA regulations are only part of the solution. We believe that portable filter machines play an important role in dealing with the current pandemic and slowing the spread of future ones. One that is easily deliverable and highly flexible in a school classroom setting. This year, we test the filter machine that was built by the TUM students last year and then optimized by Professor Martin Daumann and supervised by the Human Motion Institute. This was presented during the symposium that was held in March last year. The idea we present is to collaborate with pupils to run some experiments and test the filter machine in their school in order to capture some pictures and videos for better understanding of the performance of the machine. The work is supported by the Max Planck Institute, especially from the group of Göttingen, Professor Bodenschatz and Dr. Marie. This collaboration came along with the Michaeli Gymnasium, as the pupils there had some experience in this area. Last year, supervised by their teacher, they participated in the Jugendforschprogramm, a competition that requires pupils to do some research. Their research goal was to determine the ventilation behavior and the resulting air quality in the classrooms at the school. They examined the ventilation strategies and their effect on the basis of the obtained air quality measurements and the changes in ventilation behavior that can be made to achieve better indoor air quality.
In Eigeninitiative haben sie in einem Klassenzimmer für nur 400 € Materialkosten eine Lüftungsanlage eingebaut. Damit kann die Aerosolkonzentration in der Raumluft erheblich gesenkt werden. Die Anlage reduziert Aerosole laut Forschern des Mainzer Max-Planck-Instituts um bis zu 90%. Aber wegen behördlicher Auflagen darf sie nicht genutzt werden, obwohl Lehrer und Schüler die Leistungsfähigkeit mit aufwendigen Messungen bestätigt haben.
Dadurch, dass wir tatsächlich die Datenlage behandeln über das Projekt und wir sehen, wie effektiv es ist und relativ preisgünstig im Vergleich zum normalen Rauchlüfter, finde ich es total schade, dass wir hier eben noch kein grünes Licht bekommen haben.
The machine is tested on an artificial fog device, depending on different features like the position of the machine in the room, which can be influenced by objects around it. A tube is also included for some experiments. We also try to control the airflow by opening particular windows in a room and the door in order to enhance the performance of the machine. Then we will use some different techniques using lights or laser to take suitable pictures and videos that can be analyzed later. Different techniques of how to use the laser were suggested by Dr. Hussein Bahiri to enhance the capture of images, which can be relevant for further research. First, we use the fog machine, same as the one in theaters or discos, to produce an artificial fog in the room. Once the fog has settled in, we turn on the filter machine. For this scenario, we don't use a tube and we observe the experiment with normal lighting conditions. Here we can see the air movement and how the air is being absorbed by the machine. The machine was set on the highest level, which is 5, that reflects the speed of the fan inside. In order to see the mechanism of absorption better, we opted for the addition of lasers. The used lasers were normal disco lasers. These lasers have the ability to extend the beam in order to cover more space. Commonly used lasers do not have this ability. We use optical lenses to extend the beam to a certain size and distance. Under low light conditions, these lasers show the suction in a more visible way. Vary the power of the filter machine and get different results. As expected, lower levels need longer time to clear out the fog. We observed that for the first solution, acoustics were a problem. Level 1 was acceptable, but level 5 was really loud. For the second experiment, we add a tube to the machine. This tube has one end attached to the machine and the other positioned high in the room. The fluctuations of the temperature of the room and the lighter hot air that arises to the top lead to complex aerodynamics. This allows us to compare the performance of the filter machine under these two settings. For our measurements, we use the SDS-011 sensor and Arduino to detect the density of the particles over time. Here, we measure the density of the coarse particles denoted by PM10, which are the particles of a size between 2.5 micrometer and 10 micrometers. These particles are the most relevant, as recent studies have shown that SARS-CoV-2 exists in aerosols smaller than 5 micrometer in diameter. The red line refers to the case where the filter is off, and the green line when the filter is on. We can notice that the density of the particles decreases faster when the filter is on, reaching the density of the particles calculated for the initial state before filling the room with artificial fog. For the ultrafine particles, which are denoted by PM2.5, the slope is steeper than the PM10 particles, which makes sense because these particles of a diameter smaller than 2.5 micrometers thus can be absorbed faster by the machine. For both cases, there is a clear improvement with the filter machine. Even when compared to a scenario where windows are open, the filter machine still comes out on top. We also compared our filter machine with a Philips device, which is available on the market. The fog is absorbed from the sides and emitted through the top. The suction level was slower than our machine, but from the acoustic perspective, the Philips device was much better as it was almost silent. In conclusion, the solution tested here proved to be promising in terms of ventilating rooms in a school setting. We provide videos and photos of our experiment under different conditions. The pictures can also be further analyzed by software such as PIV View to create vortex fields that visualize precise movements of particles.
Okay, so there I think we have some extra. Okay, so Thank you very much for this presentation of this complex and broad group. I think it's impressive, and I think you have a very positive feedback, because Mohsen, he said, but he's in another meeting, but he just wrote that he would like to see the video, and we talked and we talked before. So they are interested to consider research collaborations that could build on these efforts, because they also know how difficult it is to get information from the real world, where the teachers and the pupils actually have to suffer through the lectures. And well, in the methodology, I think we have used here, and also the know-how at the school shows that one can now start to do well comparisons between different filters, to compare different settings, window open, window closed. No one really knows about this, and they also confirmed that the problem is that the only ones to come up with data or comments are the manufacturers, and of course they do have always a conflict of interest, because they should not be the ones to determine what is really best. And well, there are two comments from my side. On the one hand, I was very glad to see that it was also fun, obviously, and so if you somehow had a research team also, or the research development team in a company, well, to have a group jumping on a new box or a new product with the same enthusiasm as the students, that's about the best you could hope for. And the other part is that I was personally very happy that no one was hurt, because some of these experiments actually were kind of dangerous. So for the laser lights, we had special glasses, and there was a certain risk that you forget that you're wearing these glasses, because they really filtered out the green light to 100%. And you had the impression, wearing the glasses, there is no laser light around. And if you then take off the glasses and you would look into the laser, that could have been dangerous. So I'm very glad about this. So these are my statements. So thanks a lot to this group. Are there any questions or comments?
Maybe just a quick comment. Martin, thanks a lot for all this and for the presentation here, which I think is very important, because it makes a clear point. In the public opinion, students are usually treated as like smaller versions of grown-ups, almost like kids in school. And they first have to make a degree, and then they can do some serious work. And it shows and demonstrates that the enthusiasm and the creativity and the power that comes from students on all levels is widely underestimated. And you can really run a lot of problems and challenges with students if you find the right angle to get them excited. So thanks a lot for this activity. And I'm a big believer in the power of the brains coming from, and the contributions coming from students, also in scientific environments. Thanks, great stuff.
Thanks, Klaus.